Welcome back to my YouTube channel. Today we will discuss another question of a NET exams. Okay, question is given that f is an entire function. Okay, and consider the function g given by gz equal to f of z minus 1 by z. Okay, and which of the following statement are necessarily true? Okay, now solution. Solution. Okay, now first option say g has a pole at 0. Okay, this is true or false. Okay, now check here. F is entire function. Okay, f is entire, so now 0 belongs to also complex numbers. Okay, and f also analytic at 0, so f can be expressed as a Taylor series around 0. Okay, so now f of z can be written as f of 0 plus z into f of 0. Okay, dash plus z square y factorial to f double dash 0 and so on. Okay, and here given gz equal to f of z minus 1 by z. Okay, so that is equal to, now put the value of the f of z, so this is equal to f of 0 plus z f dash 0. Okay, plus dot dot and minus 1 by z. Okay, this is also Lorentz series at the point 0. Okay, and you also know that suppose f of z equal to this is equal to summation of n equal to 0 to infinity an. Okay, z minus z0 to the power n plus summation of n 1 to infinity bn z minus z0 to the power minus n. Okay, we already know that this is a Lorentz series expansion, okay, of a function f. Okay, and we also know if this is removal singularity at the point z0, if bn equal to all bn equal to 0, okay, then the function f has a removal singularity at z0. Okay, in this case removal singularity. Okay, and if bn is finite terms, bn as a finite terms are non-zero or not equal to 0, then in this case this is a pole. Okay, pole at the point z0. Okay, and if bn contains infinitely many terms, bn infinitely many of bn not equal to 0, infinitely many point of bn not equal to 0, in this case this is essential singularity at the point z0. Okay, so clearly here see that here only finite term is non-zero, this is 1 by z term is non-zero. Okay, so in this case at the point 0 gz has a pole at the point z equal to z0, so first option is true. Okay, now second option say if g of alpha equal to 0, then mod of alpha not equal to 1. Okay, clearly we choose for second option f of z equal to z. Okay, this is a analytic function. Okay, now gz equal to f of z minus 1 by z. Okay, so that is equal to z minus 1 by z. Now if we choose z equal to 1, so 1 equal to this is equal to 0. Okay, 1 minus 1 equal to 0. Okay, but modulus below of 1 equal to also 1. This is a contradiction. For this statement is false, because this is statement say g alpha equal to 0, then modulus of alpha not equal to 1. But here already in this example we given modulus of 1, this is my alpha. Okay, modulus of alpha equal to 1, so this is a false statement. Okay, now start statement say that g has only finitely many zeros. Okay, so we can choose the function. In this case we function f of z equal to sine z by z if z not equal to 0, and 1 if z equal to 0. Okay, so in this case the gz equal to z minus f of z minus 1 by z. Okay, this is has infinitely many zeros, so we already know that this function has infinitely many zeros. Okay, so gz equal to, when z not equal to 0, so this is equal to sine z minus 1 by z. And we also know that sine z has infinitely many point of equal to 1. Okay, this type of point n pi by 2 types of points. Okay, where n is odd numbers. Okay, infinitely many points of this equal to 1. Okay, so if sine z equal to 1, this function gz equal to 0. Okay, so if we choose f of z this type of function, so gz has infinitely many zeros. Okay, so this option also false, because here only finitely many zeros. Okay, in this option, but this is a false option. Okay, now option 4 say maximum of gz gain equal to 1. Okay, so here already given gz equal to f of z minus 1 by z. Okay, this is also can be written as z into f of z minus 1 by z. Okay, so now first we choose hz as follows: z into gz. Okay, so we have this is equal to from this z f of z minus 1. Okay, this is also analytic every point of complex numbers. So this is also entire function. Okay, we check maxima at the point where at the circle z equal to 1. Okay, now in this is a entire function. Okay, now in this z equal to 1, z less than equal to 1. Okay, now we choose z less than equal to 1. Okay, in this domain the function hz maxima at the boundary point. Okay, boundary point of this domain. Okay, this is called the maximum modulus theorems say. Okay, so this is maximum at the point z equal to in the boundary point. Okay, but if we put z equal to 0, this is equal to minus 1. So mod of h0, this is value equal to 1. Interior point of this domain equal to 1. Okay, already contains modulus value equal to 1, but maximum but maximum modulus theorem say that it is maxima at the point of boundary point, only boundary point. So this implies maximum of z less than equal to 1 hz getting equal to 1. Okay, this is not equal to 1. Okay, this is getting equal to 1 by modulus maximum modulus theorems. Okay, so and also maximum of this is also equal to maximum of modulus value equal to 1 hz also equal this value. Okay, this is also getting equal to 1. Okay, so now put the value of hz. So hz we consider as follows this. So put this value. So we have maximum of modulus value equal to 1 z gz also getting equal to 1. Okay, so this equal to maximum of z equal to 1 and the put the value of modulus z equal to 1. So we ultimate this equal to gz modulus gz, this equal, this is also getting equal to 1, hence the proof. Okay, so this is a correct option. So answer of the question is 1 and 4. Okay, thank you.